All right. Today I plan to try to finish topic 6. I'd like to wrap that up so that we can move on to the next chunk of material. Next chunk of material, I think what I would like to do is principal component analysis. Hey Taylor, I haven't seen you in a while. Principal component analysis. That won't be on the exam because we don't have time for you to do any homework on that topic before the exam. But the exam is next Wednesday. Remember, I made an announcement Monday about what that's going to look like. It's going to be R-based. You will have 2 of 3 types of problems. One will be vector or matrix basic operations. One will be simulation exercise using the multivariate normal, and one will be t-squared based inference on a mean vector. Question?
Oh yeah. So are we using do we use like computers here, or like these computers, or our own?
You can use whatever computer you like. You're welcome to use this computer in here or bring your own. Free to access any resources except for a live person. FYI, I wanted to share something from my personal work right now. I collaborate a lot with people in other departments on campus, from the medical school to electrical engineers to biology and other things. Right now I have a collaboration with a PhD student in the vet school, and he has multivariate data. So I just wanted to share a real-world example where this stuff that we're talking about right now, t-squared inference, is the scientific interest of the study. So he has dogs. And for each dog, there are 2 diets and 5 numeric response variables. For each dog, they are given a diet, a type of food, and then 5 numeric variables are measured on them. Each of these variables are quantifications of different chemical byproducts, like triglycerides and other chemical compounds that are floating around in the bloodstream. And the interest is, what's the difference between these 2 diets in terms of these health indicators? One way to go about this problem is the usual STAT 101 univariate style. That would look like go to each variable, triglycerides say, and if we have, say, 10, I think we have close to 20 dogs. One possibility would be pick one of the variables, triglyceride abundance, say, and do a 2-sample t-test comparing the dogs in diet A to the dogs in diet B on that one variable. And that's what he has done so far. He's got univariate t-test based inference. And so 5 p-values, 5 confidence intervals, 1 for each of these variables. But also of interest, or maybe even of more interest, is can we assess simultaneously, do all 5 of these things? What's the behavior of all 5 of them between the 2 diets? If all 5 of the variables are all kind of measuring health in some way, they're different, but they're all targeting the same basic physical characteristic, then it makes sense to consider them all together. Is the health impacted by diet, yes or no? That's a multivariate question. So his let's call the variables x1, x2 through x5. And suppose that there is a mean vector that corresponds to each of these variables. So in the population, there's a mean. In fact, we may want to specify there's a mean in diet A and a potentially different mean in diet B. So a natural way to do inference would be one or the other or both of a hypothesis test and a confidence region or a set of simultaneous confidence intervals. What we're doing for sure is testing the null hypothesis that these two means are the same. That's the 0 vector, 5 elements in that vector. Suppose I wanted to test that. What's the difference in two mean vectors? Based on what we've seen in class, how could you go about doing that? What technique do we know for testing a difference of mean vectors? If these were univariate means, you could just say two-sample t-test. We have mean vectors, though. What's our analog? What's our multivariate analog of a two-sample t-test? From topic 6, topic 5 told us about the t-squared test. And then topic 6 extended that to the two-sample problem. T-squared test is a generalization of the univariate t-test. So let me go to slide 22. If you want to test what's the difference between two mean vectors, it's not a univariate t-test because it's multivariate data. But there is a generalization of the t-test. It's the t-squared test. So we could compute this statistic and, under the null hypothesis, compare our statistic to this reference distribution. So we're going to do this using what we could call the two-sample t-squared test. And similarly, if we wanted a confidence region and or simultaneous confidence intervals. Those come directly from the t-squared result. What's an important assumption? If we're going to do this to this real data set, we have 20 dogs. What's an important assumption that we need to consider before we do a t-squared test? Do we need to worry any about the population distribution? Like what type of distribution underlies our data? What do we need it to be for the t-squared? Okay, the multivariate normal, right? Just like with a univariate t-test, we need the population to be univariate normal. For these multivariate t-squared tests, we need multivariate normal. Or what are a couple of options? Huh? Bootstrap is an option. If I have 20 dogs and I'm not confident that the population is normal, I can get p-values and confidence regions and confidence intervals via the non-parametric bootstrap. By resampling from the data, I can get a valid p-value and confidence statements without requiring the multivariate normal. That's what I'm actually going to do with these data. Because there is some skewness to the data. The sample size is relatively small. So I am kind of concerned about whether the population distribution is normal. What if the sample size was really big? Like suppose we had 500 dogs. Anything new as an option? Or any new issues or lack of issues? What would happen if the sample size was 500 instead of 20? Somebody said central limit theorem or large sample results. Yeah, with a large sample size, a lot of the time you can do approximate statistical inference without requiring some assumption, like the multivariate normal assumption. In our notes, we saw two-sample t-squared test, looks like this, and we compare to this scaled F. But if we have a large sample size, we can compute basically the same statistic, and instead of comparing to that scaled F, we can compare it to the chi-square. Approximately, with a large sample size, no matter what the population is, the t-squared statistic is chi-square. In our case, we don't have a big sample size. I'm not comfy with the multivariate normal assumption, so I'm going to use bootstrap. All right. So let's see. I was going to show you that I can't remember if I went through this with you or not, but the container data set that we saw in both topic 5 and now in topic 6 contains code illustrating the two-sample t-squared test. So let me just walk through this script. We've seen at least the first of the script. These are elemental concentrations of 9 different elements in these shipping containers. We actually have 2 different types of shipping containers. And we have a sample size of 10 for each container type. Step 1, if we're going to do multivariate inference on a mean vector with a small sample size, especially, we need to consider whether the population distribution is normal. So that's what we started with. I did QQ plots and then a multivariate assessment of normality. So then I'm pretty sure we've seen this. In the case where if I just want to do inference on one mean vector, like the mean vector for container type 1, if I just wanted to look at container type 1, then that's a one sample t-squared test. That's topic 5 stuff. So I can compute t-squared and a p-value as a right tail probability in a scaled F distribution evaluated at my t-squared. Similarly, we could put together confidence regions and confidence intervals. Here are simultaneous confidence intervals, both t-squared style and Bonferroni style. And then what's new begins at line 193. This is the two-sample t-squared test. So in this case, we're going to ask container type 1 compared to container type 2. Let's test, is the mean vector the same? Is there a container type effect? So this code through here is implementing what's in our topic 6 notes. The 2 sample t-squared statistic, this thing here, involves sample mean vectors. X bar 1 is the mean vector for comparison group 1, and X bar 2 is for group 2. Delta 0 is what we hypothesize the population mean difference to be. Typically, that's 0, the 0 vector. And then we have to compute this pooled covariance matrix, which is defined on the previous slide. So in my notes, here's computing the pooled covariance matrix. Here's computing the 2 sample t-squared statistic. Here's a p-value. Just like above, it's a tail probability in a scaled f. There is a built-in function that you can use for 2 sample t-squared tests. My recommendation when working problems like this is to do it manually, like write your own code just like I did up here, and use a built-in function. You should be able to match the built-in function. And then you have a little bit of confidence that comes from being able to do it yourself. And it's always good to match what a built-in function does. Okay, so C container script for some example code for doing t-squared stuff, both 1 sample and 2 sample. And then while I'm on the topic of examples, there's 2 other scripts that are relevant to topic 6. One is called nursing homes. And I'll talk about this one today a little bit. We have multivariate data on a bunch of nursing homes. There are 271 privately run nursing homes, 138 that are nonprofits, and 107 that are run by government agencies. For each one of the nursing homes, we have p equal to 4 numeric variables. The first one is, how much does this place spend on nursing labor each year? The second is, how much do they spend on dietary labor, so like the kitchen and cooks and such. Third one is the cost of plant operation and maintenance, just maintaining the facilities and all of that. And 4 is cost of housekeeping and laundry. We're going to characterize each nursing home in terms of fiscal efficacy or efficiency using 4 variables. And then the inferential question is, what differences, if any, are there across these categories of ownership type? This is actually a 3 comparison group problem. It's not a 2 sample t-squared test, because there's 3 categories I want to look at. So it's not a t-squared assessment. T-squared is when you have either one group or 2 comparison groups. But when we go beyond 2 comparison groups, that's where we need the ANOVA kind of functionality. So multivariate ANOVA, and I'll lecture on that a little bit today. Nursinghomes.R walks through MANOVA calculations. So basically, we're going to learn how to compute a p-value for testing. Does this mean vector remain unchanged across the private, nonprofit, and government-owned nursing homes? Is there any difference in the mean vector between the 3 ownership types? And just like we did with t-squared stuff, we are able to construct component by component simultaneous confidence intervals. We can also get confidence regions. I show in the script how to do confidence intervals, simultaneous confidence intervals. So we could ask for variable 1, what's the difference between the government-owned and the private-owned? And for variable 2, what's the difference between nonprofit and government-owned? Any paired difference, we can construct an interval for it. The other script and data set that is relevant is the plastic film data. So these are data on certain qualities of a type of plastic. There are 2, quote, factors in this case. In the nursing home data, there's 3 comparison groups, and we would say we can define the 3 comparison groups in terms of 1, quote, factor. And all I mean by factor is a categorical variable. The categorical variable in this case, there's only one of them. It is type of ownership. So there's one categorical variable. It happens to take 3 values, either private, nonprofit, or government. That language of factor should bring to mind ANOVA stuff, the univariate ANOVA stuff that you learn in STAT 101. Remember that there's a one-way ANOVA and there's a two-way ANOVA and beyond. But the STAT 101 typically shows you one-way and two-way. One-way ANOVA is when you have a numeric response variable and one factor. The factor is a categorical variable, like treatment A or treatment B, type A, B, C, or D. But it's just one variable whose levels define the comparison groups. When you have 2 factors, 2 categorical variables that define categories and subcategories, that's a two-way ANOVA problem. And we'll see there's a one-way MANOVA and there's a two-way MANOVA. In the dog example, we could make it a two-way MANOVA problem if, in addition to diet being the main factor, in addition to that, if we looked at, say, gender, each dog is given one of the 2 diets, and each dog can be characterized by one of 2 genders. So there's 2 factors, diet and gender. The plastic film data are an example of a 2-factor problem. For each sample of this plastic, there's 2 factors. One of them is called rate of extrusion, and the other is about the amount of an additive. Both of these are categorical variables. That's what a factor is, just a categorical variable. And both of these factors have just 2 levels, low and high. So there's low levels of extrusion and there's high extrusion. There's low additive, there's high additive. That means there's 4 treatment categories. There's low on extrusion, low on additive, there's low-high, there's high-low, and there's high-high. With these data, we have 5 samples within each of the 4 comparison groups. So we have 5 samples of low-low, 5 of low-high, and so on. And then we have multivariate data. P is equal to 3. Our variables are tear resistance, gloss, and opacity. So this code is an example of MANOVA, and specifically an example of what we're going to call two-way MANOVA. This code, by the way, has an example of using a built-in MANOVA function. I think it's good practice as you're learning about this stuff for the first time to take a crack at computing the statistics and p-values manually, and then computing it using a built-in function and making sure you can match. That's a good exercise. So there is a function called MANOVA that can do this MANOVA stuff for you. But I've also given you code that does it manually. Okay. So here's where I want to go with the rest of today, beginning at slide 28. We now know about t-squared stuff. You can do one sample or two sample t-squared stuff, depending on whether you want to do inference on one mean vector or a difference of mean vectors. What happens when you have more than two comparison groups? That's an ANOVA type problem. Because we have multivariate data, it's a multivariate ANOVA type problem. What I'm going to do on the next few slides is motivate the multivariate ANOVA model. And to do that, I'm going to harken back to the univariate ANOVA model. This stuff on the next couple of slides is all about the STAT101 ANOVA model. You don't have to follow this perfectly, but get the gist with me here. We have data like this. Here's notation we're going to use. Remember when we did the two-sample t-squared test, we said we had x11, comma, x12, dot, 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 some number of observations in comparison group 1. And then we had x21, x22, dot, 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 some number of observations from group 2. In the MANOVA setting, we have 3 or more comparison groups. So we're going to write like this, xl1, xl2, dot, 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 a sample from comparison group L. And we're going to say there are G comparison groups. In the nursing home example, there's 3 comparison groups: private, nonprofit, and government. All we're saying is we have a random sample from each one of our comparison groups. A little bit different from the way we have presented things so far is to write down a model. This is a model that says the population mean in the L comparison group is equal to an overall mean plus a deviation or treatment effect specific to the L comparison group. So this is an assumption. We're going to model the means for the different comparison groups with this representation. All models are wrong, but some are useful, is a famous kind of tongue-in-cheek quote of math and statistics. The ANOVA model is widely used. It is a model. It's got assumptions in it. Let's assume we can decompose the means this way. Let's then assume that the data we observe x's. For example, xlj would be for comparison group L, the jth response. And we're going to write that using what we wrote down up above. We're going to say that what you observe for the jth individual in the L comparison group is equal to an overall mean plus a treatment effect that applies on average plus a random error term. So that's just saying, as we sample from the L comparison group, we're getting data that's bobbing around the mean for that group. It's mu plus tau, that's the mean, the average, if we were to sample many, 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 many times. But what we actually see is not the exact average. We see the average plus or minus random deviation. This E represents the random plus or minus. Okay, so that's just a model. It's like a regression model if you're familiar with linear regression. We're saying some variable that we observe is written in terms of parameters plus random variation. In ANOVA, we start with this model statement in the middle of the screen. This is our model statement. And then the way that we proceed to estimate and do inference on the model is that we divvy up the variation we observe into different categories. If you remember the whiteboard drawing that I did with the side-by-side box plots, and said that ANOVA is all about comparing how different are the box locations for the different categories relative to how variable are the boxes themselves. Are there big group differences relative to differences within a group? And we talked in terms of between group variation and within group variation. So what the next slide does is eventually give us an expression about how variation in our data can be broken into pieces that speak to between group variation and within group variation. So let me just jump to this expression here. The core relationship that ANOVA is built on is that you can take a what we call a total sum of squares and write it as the sum exactly of a sum of squares that speaks to between group variability plus a sum of squares that speaks to within group variability. When I think ANOVA, I always think the side-by-side box plot picture. Imagine side-by-side box plots. We're going to decompose the total variation in all the data points into a piece that is just about how the boxes themselves differ, and another piece about how wide the boxes themselves are. We say that the sum of squares total, or also called corrected, equals the sum of a sum of squares for treatment and a sum of squares residual. Another way to say this that I think is a little more intuitive is the between group variability and the within group variability. If you look at these expressions, the total sum of squares is just a adding up of all squared deviations of the observed data points from the global mean. This x bar would be the average over all observations in our data set across all groups and everything, the total average of everything. So this SS total is kind of like a variance. We didn't divide by anything, but it's like a sum of squared deviations, which is like a variance of the data points themselves relative to an overall mean. So it's like total variation. The between group looks like a variance of the group-specific means. It's a sum of squared deviations, which is like a variance, but it's comparing the means for each group, x bar L, to the global mean, x bar. So this between group sum of squares is quantifying how different are the group-specific means themselves. What's the between group variation? And then the within group variation, it goes group by group. This first summand is over the groups. And it considers the sum of squared deviations about the group-specific mean. So it looks within groups. It goes to the Lth group and asks, what's the variation in this group? Add that to the next group and the next group. Total variation, we decompose it into a between group variation and a within group variation. And then we have this table. This is the STAT 101 ANOVA table. Any statistical software will show you this table if you ask for ANOVA. Analysis of variance is all about analyzing and comparing variances, sources of variation. The table is just a presentation of the model decomposition I showed on the previous slide. We typically say, here's a column that specifies the source of variation, and it's either treatment, that would be like between group variability, or residual, that would be like within group variability, and total. For each category, we write down the sum of squares. There's sum of squares total down at the bottom. There's sum of squares for treatment, and sum of squares for residuals. And there's a certain number of what are called degrees of freedom that go with each. We don't have time to go into the details of degrees of freedom, but if you've always wondered what in the world is degrees of freedom, there's actually a good geometric explanation in the notes. This comes from another multivariate statistics book called by Johnson and Wickern. But there's a way to think geometrically, kind of visually, about this idea of degrees of freedom. For each one of these variability estimates, there is a separate degrees of freedom. And in ANOVA, as with anything, if you want to do statistical inference, in particular if you want to test a hypothesis, a null hypothesis, you write down your null hypothesis, and then you need a test statistic, something that you're going to compute that quantifies how much evidence is there against the null hypothesis. Our null hypothesis in univariate ANOVA is that, remember, our model statement said the mean for group L can be decomposed into a global mean and a group L specific effect. In ANOVA, we're asking, is there any difference in the means across the groups? Does treatment have an effect on the average? Does diet have an effect on the average? So our null hypothesis is that all those treatment effects equal 0. Under the null hypothesis, there's no difference in the average across the comparison groups. That's our null. And our test statistic is an analysis of variance kind of statistic. It is sum of squares treatment divided by sum of squares residual. Excuse me. You can think of this as like a ratio of the between group variability to the within group variability. Again, going back to the side-by-side box plot picture, that's what ANOVA is all about. How spread out are the boxes relative to how fat are the boxes? So this is your test statistic, and under the null hypothesis, we know what the reference distribution is. It's an F distribution. That's ANOVA. Hopefully review. This is MANOVA, multivariate ANOVA. It's got lots of notation and stuff, but conceptually it's just like ANOVA. Here's how we write it. We say that the vector we observe for the jth individual in comparison group L, XLJ. Multivariate data, so this is a vector. Every observation is a vector. We write this analogous to the univariate ANOVA model as an overall mean, mu, vector, plus a treatment L effect, tau L, a vector, and a random deviation vector. In the ANOVA model, I didn't emphasize this, but in the ANOVA model, there's an underlying assumption that your data, these E's in particular, are normally distributed. That's the classical normal ANOVA assumption. And this F distribution that's mentioned at the bottom depends on that. The corresponding assumption in the MANOVA case is multivariate normal. So we assume that our data, or specifically these deviations, are multivariate normal. Another key assumption in ANOVA is that the variances are the same in each of the groups. Let me draw our side-by-side box plots one more time. We have a categorical factor that takes 3 or more levels, and then we have a response variable. And ANOVA is all about how do these means, the red middles of the bars, how do those differ, group-specific means, how do they differ relative to or scaled by how fat the boxes are themselves or how tall they are. An assumption of the model is that all the groups, A, B, and C, all have the same variance. So it's not that A is really variable and B is not so much and C is in between. The model assumes that they're all equally variant. And we have a similar assumption in MANOVA. I say in the notes here that the distribution in the Lth comparison group is multivariate normal, but its covariance matrix does not depend on L. There's no subscript L. So as with univariate ANOVA, MANOVA assumes multivariate normality and a constant covariance matrix across the comparison groups. Suppose that we had data, multivariate ANOVA type data, but we weren't comfortable with the assumption of multivariate normality, and maybe we weren't comfortable with the assumption of equal covariances. Just like I asked earlier in this class, what might be an alternative option for us? Just based on what we know so far. I want to do MANOVA type problems because I have 3 or more comparison groups. But the assumptions of the model, the multivariate normality and maybe the equal covariances, are suspect. What technique do we know that could get around that? It's the same technique you told me earlier today. Bootstrap. Bootstrap is a very general routine that for an arbitrary model, you can get non-parametric inference. So this that is presented in your book and in the notes is the classical version of MANOVA, assuming multivariate normality, assuming constant covariance. But in all of these instances throughout the class and through all the statistics you learn, always keep in the back of your mind there are options. Bootstrap is a very general option. So let me just jump to the punchline here. Here's slide 36, and just like with ANOVA, we decomposed the total variation into variation across groups or between groups and variation within groups. We do the same thing conceptually in MANOVA. Here is a total variation of some sort that's decomposed into a between group variation and a within group variation. Because we have multivariate data, the way we define variation is more complicated. There's not just a variance, because we don't just have one variable, one response variable. We have a vector of them. So the analogous way to talk about variation with vectors is with covariance matrices. So instead of decomposing like the total variance into a variance between groups and a variance within groups, we're going to decompose like a total covariance matrix into between group covariance and within group covariance. And then what we do as a test statistic, it's not exactly the same as the ANOVA case, but it's similar in spirit. This ANOVA stuff is all about how much variation is there between groups relative to the within group variation. And the I think most widely used statistic is actually this one for MANOVA. And see what this is a determinant, like think of determinant of a matrix as like the magnitude of the matrix, roughly speaking. So a determinant or the magnitude of the within group variability divided by the magnitude of the B plus the W, so the total. Because of the way this is constructed, we'll actually interpret small statistics as evidence against the null hypothesis. This has a special name. It's called Wilks lambda. If you use SAS or JUMP or even R, sometimes you'll see Wilks lambda in the output. It's a multivariate ANOVA-based statistic. One thing that's complicated about MANOVA is there's different ways of doing it. Depending on the setting, the math is more complicated in MANOVA than in ANOVA. So whereas in ANOVA we had this F statistic that we compared to an F distribution, in MANOVA, depending on the setting, like is it a bivariate case with 2 or more comparison groups, or is it bivariate with 3 comparison groups exactly? Depending on the answer, there's papers throughout the last several decades of people working out the math of the actual sampling distributions to use. And depending on what software and what program within the software you use, they'll be using different results. For our purposes, I want you to get the idea that MANOVA is all about comparing variation. It's between group to within group, but we do it with covariance matrices. We compute a statistic. This is one that we could use. And then we just ask, as always, is our observed statistic extreme enough to reject the null hypothesis? The specifics of how that p-value is computed can be complicated, which is one reason it's nice to have a built-in named MANOVA function. Okay, so lots of good stuff there. I think we can wrap this up. I'm going to skip testing for equality of covariance matrices. I'm probably going to skip two-way MANOVA. It's just a lot of math. And if you're familiar with two-way ANOVA, it's just like that, except with multivariate cases. And it's definitely something that you would like software to do for you, because the notation is complicated. So I don't plan to go through the two-way MANOVA, and I'm not going to go through profile analysis. We can skip that. I'll say something very briefly about repeated measures. And I'll say something very briefly about multivariate linear regression. Okay, so we'll definitely wrap up topic 6 on Friday and hopefully start on our next batch of material, which will be principal components. Okay, sorry to keep you a couple minutes late. See you Friday.